Galactic systems have implemented the cargo transportation system in Moncton, and the residents, along with Mayor Montgomery, have been very excited to see the success of the system. However, Moncton residents who work at the research center noticed that the process of receiving cargo is time-consuming, laborious, and inefficient. The conveyor scanning system, which brings goods into the research center, is not yet integrated into the building's architecture, which makes for an inefficient, non-user-friendly design. Mayor Montgomery has proposed rebuilding the research center to allow for the conveyor scanning system to be seamlessly integrated into the architecture of the research center to add productivity and user safety. The center has a zipline transportation system which brings goods in from the distribution warehouse. Once the zipline is detached from the cargo, it's taken by the conveyor belt through the airlock, past the security scan, and then into the research center. The research center features 2 lab areas, a lunar materials advancement lab and a lunar exploration lab. The lunar material advancement lab is dedicated to finding use in materials found on the moon, converting them into valuable materials like fuel or construction materials. The Lunar Exploration Lab is dedicated to exploring the physical and chemical makeups of specimens found on the moon and developing new plant organisms to grow in Moncton's hydroponic farm system. There are 20 researchers working in the labs on any given day, and a further 5 employees filling other tasks in the research center, including monitoring the server home and managing logistics, including inbound and outbound deliveries. 10 of these employees opt to work a 2 days on, 2 days off schedule, and are offered to stay at the research center overnight to avoid the daily commute from the resettlement center. The research center is located 750 meters from the farm, 800 meters from the distribution center, and around 11 kilometers to the mine and manufacturing center.
Before beginning the research phase, a list of key design drivers was identified. These included being adaptable to various cargo types and sizes, being easy and safe to use, made from sustainable and locally sourced materials, a minimised need for manual troubleshooting, being effective and efficient, and adaptable to expansion. Further to the key design drivers, we also identified a list of critical functions. These included a low need for manual troubleshooting, an integrated scanning system, remote operation, good suitability to the lunar environment, and live updates to alert of any security threats.
Based on our initial understanding of the problem context and the defined critical functions and the key design drivers, the how might we question was asked. How might we provide a design solution for Moncton which integrated the existing security scan and ensure safety, efficiency, and adaptability to growth? We carried out some research to benchmarking existing designs applied both on Earth and on the Moon. These included airport security systems at international terminals, large-scale post office conveyor systems, and a range of train station terminals. This helped us to frame our thoughts leading into the ideation phase.
To begin our ideation, we identified an initial user journey map as shown. The journey map of the package begins at the loading dock, is taken by the conveyor belt through the security scan, which determines if the package can enter the research centre. If the cargo is approved, it goes through the airlock and into the storage area. Based off the journey map and the user needs of the research centre, Galactic Systems devised an initial bubble diagram of all necessary areas of the research centre. These included the lab, the loading dock, the entrance and the airlock, an emergency shelter, a medical bay, a mindfulness and recreational room, an oxygen concentrator module, server room, toilets, storage, dormitories, a meeting area, a break room, and a kitchen.
After some initial design work, a circular floor plan was developed, featuring supporting rooms that surround the main lab area. However, this layout presented several drawbacks. The kitchen proved to be too inaccessible for its anticipated frequent use, and the dormitories were positioned too close to the workspace, potentially disrupting users' work and life balance. Additionally, the circular design could lead to inefficient use of space and complicate future expansions of the structure.
Galactic Systems decided to have a look at some other shapes to apply to the floor plan that would better achieve our design drivers. We found octagons to be a great solution as they're adaptable to modularity and with the same perimeter as a square provide around 20% more space, which is cost efficient for Moontown. Learning from the initial circular floor plan, we applied the rooms to an octagonal layout. We also added an elevator to the storage room, right after the airlock. This will allow for heavy cargo to easily reach all 3 levels of the centre with ease, as well as allow the employees to move between floors. We tested the efficiency of the octagonal design by comparing 3 user journeys in the initial design to the revised octagonal design. All 3 user journeys were drastically simplified with the octagonal design and rearranged rooms. We prototyped a 3D version of the design using 3D printing. While this model confirmed the success of the modular aspect of the design, each level was a little bit too tall, inefficiently using limited resources. We produced a second prototype using cardboard, which efficiently uses space and material to provide the workers at the research centre a safe and easy to use workplace. Each module of the building will be constructed individually using lunar regolith in conjunction with steel and aluminium acquired locally from Moontown's mining facility. Any exposed steel or aluminium components will be covered in a thermal control coating used to protect from radiation and heat. The modules will be placed by the crane which was used to construct the existing buildings in Moontown. The edges of each module have an airlock mechanism which allows them to join with other modules, providing an airtight space across the entire research centre. The area around the conveyor belt that operates externally is surrounded by a moon glass exterior to protect from the moon dust affecting operations. The final user journey map of the cargo is as shown. The package begins at the loading dock, where it is taken inside of the conveyor area to be taken through the security scan, which determines if the package can enter the research centre. If the cargo is approved, it travels on the belt through the airlock and into the storage area. The employee working inside of the research centre refers to the scan, which allows them to identify if the package is for floor 1, 2, or 3. They then take the package via the lift and leave it in the relevant storage area for access when needed. If the security scan is denied, rather than going through the airlock, the package is directed to an attached quarantine container where it awaits inspection by a safety expert to advise how to proceed. The design solution is viable given the materials will be sourced from the Moontown's own mining facility, and the modular nature of the design allows for the initial build to offer enough space for the current operational requirements while creating an opportunity for expansion once the research centre's needs grow. The initial procurement of materials and construction of the proposed design is projected to cost around $3 million. The research being carried out in the centre is invaluable, along with the safety of all users. Moontown has the opportunity to make a strategic investment in the research centre to facilitate advancements in lunar knowledge.